now for something completely different. My agents are people. So I will have reinforcement learning and I will have multi-agent. I will not have multi-agent reinforcement learning, but hopefully it will be somehow related in your own mind. So I'm going to talk first about a single agent, the curious one. So I'll talk about curiosity, which is a kind of intrinsic reward reinforcement learning. And then I'll talk about two agents. One of them is a person and one of them is a robot, which also have, again, reinforcement learning inside. And then I'm going to talk about a group of robots and a single person, and then a single robot with a lot of people. So I have a lot of combinations of agents and reinforcement learning. So first I want to define curiosity. So I'm the head of the curiosity lab in Tel Aviv University, somewhere. So there are a lot of definitions of curiosity. I love this one because it's mine. So it's an intrinsic drive to learn as much as possible in accompanying behavior. So curiosity is an intrinsic drive. Everybody are curious from within. You can give a curiosity pill. You can obviously destroy it. It's called the educational system. That was a joke. I'm going to have some jokes. Okay, sorry. To learn as much as possible means that for a curious agent, for every answer, there's a new question. So it's like hunger. If you're hungry, you eat, but then you're hungry again. So you use what you learn in order to learn more. And accompanying behavior means that you cannot be passively curious. Curiosity is about the action itself. So once you have definition, you have this model. And this model have curiosity about two things, about learning and the behavior. So here you can have, as a learner, you can have whatever learning model you want, neural networks, Bayesian inference, whatever you want. The most important thing is that you can quantify how much you learn. So in neural networks, you have the loss, and in Bayesian inference, you have the divergence, information gain. And what we have on the other side is the behavior, which is the reinforcement learning. And the difference between, I think, almost everything we saw before is that you had an extrinsic reward function, somebody trying to optimize something that someone gave it to you. And in curiosity, it's the how much you learn is the reward that you get. And I'll give like a very example. If you give this to a child, to a baby, what it will do, it will put it inside your mouth, and it will not get any reward because it's not that interesting. So it puts it in the mouth, did not get reward, did not learn anything, so it will not get any reward. But if it presses the red button, then usually when you press the red button, something happens. So they press the red button, something happens, they learn about the environment, so they get a reward about pressing red buttons. So that's why children always press buttons, because they learn that pressing buttons is informative about the environment, and this is how they got reward. I won't go into neuroscience, but neuroscience also shows that the pathway for actually curiosity is also the dopaminergic circuit. So when you get new information that you're interested in, you actually get dopamine as if you ate chocolate. And very simplistically, because I don't have a lot of formalism here, it's a very high level thing. So the more information you get, the more reward you get, and then you write some code, and then you go to robots. So this is my first robot. So this is a single curious robot. So obviously you recognize the robot, Lego. So it's a very simple robot. It has 1 degree of freedom for the arm, 1 degree of freedom from the camera and the brain. The brain doesn't come with the Lego, it just happened to be in my lab. And then the robot is, so the question here is, what can the robot learn by itself? Only by using curiosity. So it can learn sensory motor correlations. So it moves the hands and it can learn about what it sees. And then it uses what it learns actually to learn the second order correlation. And what in the end it actually learns self-recognition. So what self-recognition, I'll give it a picture, it's 1 and 0, 1 where it is, 0 not. And it just learned the correlation of if something moves in the visual field and I move my arm, then that something is me. So I can predict what I am, and this is actually self-recognition, which is really cool. But then we also apply this curiosity algorithm, which means a reinforcement learning algorithm, where the reward is how much you learn. So you start with random actions, and then you get reward if you actually manage to learn, to predict these kind of things. So I give an example of two wrong behaviors. So one of them is not moving, because if you don't move, you don't see any movement in the field. But also moving like this is not correct. So the robot actually learned by itself to watch its own moving hand and gets reward. So the convergent behavior was actually the robot moves the hand and follows it with its own eye. And the really cool thing is that there is a developmental stage in infants when they actually recognize their own body and say, "Ooh, that's cool, that's me." So the robot actually reached that educational stage. Yes.
Sorry, when you say that it learns it, you mean that like you have some specific thing you have in mind of what it is?
Well, actually,
there's prediction.
Yeah, there's prediction. So I'm trying to predict like the motor behavior or the sensory behavior. So I have a 2-to-1 correlation between the sensors and motors and try to predict one of them. Actually, the question was, well, you didn't ask, but I'll ask myself, is this robot actually try to learn everything it can exhaustively? Like it has like 8 streams of information. It was at 168 neural networks running in parallel with pruning and blah, 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 but reinforcement learning was done on this one. So this is actually, again, a robot that learns by itself. And in the end, it actually learned a lot of things, and it can do reaching for a moving target. And actually everything is self-learned and decided by itself by the algorithm, and if you call it self-learning, then if it actually changes, so I destroyed the read the channel of the camera and I destroyed a little bit of the motor, but because it's self-learning, it actually overcome this thing and actually came back to the yes, it actually qualifies as deep learning these days, but it was in 2009, so that word wasn't invented. Okay, so we had a robot, now a robot and a child. This is the educational robot, so it's called social robot. I don't know how many you know about social robots. Social robots, the purpose is to do social things. They don't pick up things. I know it's hard. People are easier. So they do like social things. So this robot is actually, it's a robot and a child playing together on a tablet. The robot is not a teacher, the robot is a peer, so they learn together. And the tablet is like an educational app to learn Spanish as a second language for children. They learn Spanish, who cares? What we actually had here is the recognition of facial expressions of the child. So we knew whether it was smiling or engaging or stuff like that. And we got this as a reward to the robot. So the goal of the robot was actually to make the child happy while learning Spanish as a second language. You try to be happy learning Spanish as a second language, very hard. So the goal was actually to do this kind of reinforcement learning. The actual goal, I'm using code, yes, was to overcome what's called the novelty effect. So I know this robot looks cute, but robots are super boring. Like every toy, if you play with a robot, it's very cool. The second time it's boring, and the third time you just don't care. So it's called the overcome the novelty effect. And here we had a long-term interaction. It was for 2 months. Once a week, this robot actually interacted with the robot and slowly adapted to what it had. I forgot to say. So the actions of the robot were actually the social behavior of the robot. So which faces it did and what were the motivation strategy, like a good job, let's try something new. So it learned for each robot, for each child, what will be the motivation strategy. And that's what's called actually personalization. We call it affective personalization. And the concept here is to actually personalize, so it's a reinforcement learning. It was a different policy for each child. So it's actually to learning the educational policy for each child to actually learn these things. And
from scratch, or like
the what?
From scratch to learn, like this is a new.
No. So actually, so the actual comparison was with best practices. So we actually we converted the best practices of what to do to a policy, and that was the starting point. And from there on, we started personalization. It wasn't from random; it was from best practices. And you can, again, it's children. It's very low ends. And getting a statistical significance something is very hard. So this was 2 months in a kindergarten every day running with robots. So this is a single child and a single robot running reinforcement learning together.
Can I ask you a quick question?
Yes.
What's the scale of number of steps?
Okay, now doing all these things you are not allowed to do in reinforcement learning. So obviously the biggest problem with reinforcement learning is the number of episodes you need. And the number of actions and stuff, you need like, millions and stuff, and here we didn't. And actually that's one of the reasons reinforcement learning is not used in human-robot interaction, because you just don't have enough. And we don't have a simulator for humans, because if we had that, then we'd just be out of a job. So that's actually very hard. The only reason I did it actually worked and actually differentiated is because I did something which is not allowed, which is use a very large learning rate. Usually for reinforcement learning, you have to do a very slow learning rate, and you have a lot of episodes and it's slowly converging. We had here a very, very, very large learning rate, which, I would flag the test, the exam if I did that in a test. but that was the only way to actually have some divergence. And it obviously, you can actually see in the paper that it did not converge to
The
anything.
reason I'm asking is my colleagues did something similar and we had an argument. So we have
I would love to join your argument. Contrastive explanation about this. So we could actually see that it did not converge to anything yet, but we could see that each child had a different policy, and we did so like effect on the actual behavior of the children. So that's what's important. Yes, so that's a single curious robot to a single child. So let's move with a group of robots. If we have multiple robots, why not? So it's still curiosity, but not necessarily RL. So here we are interested in actually the person's RL policy. So what we have here is the 3 robots, which are either friends or not friends of one another. And we're trying to test the social curiosity of the person. So we're actually building a model to simulate the person. We want to understand is the person curious or not. So it's measuring curiosity, social curiosity of a person. So each robot is either a friend or not, and they express their friendship via non-verbal interaction. So if they're friends, like nodding and yes, and if they're not, then fist and don't look at you. And the person has an eye tracker, so we know which robot the person is looking at. So the person needs to understand who's a friend of whom. And what we did like a very quantitative way of quantifying how much informative is each non-verbal behavior. So we ran an Amazon Mechanical Turk of saying, see this video, is it good or bad? And what is interesting here is there are very positive ones, and there are very negative ones, like the fist, but there are also like ambiguous ones. So it is actually like the amount of information is different, and not what type of information. And we actually use this to model the person, in the sense that if the person is looking at this robot, then it automatically knows that he's a friend of someone. And if you look at this, he doesn't actually know. So we actually had the Bayesian update of the person's model of what it's going to do. And then we actually modeled what we were interested in was in the behavior of the person. So we wanted to see whether the person is optimally curious, in the sense that is it behaving in the way to solve this problem of, I don't know. So it is over time, and this is the error matrix of who's friend of whom. So this is don't have behavior, don't improve. This is the participant's behavior. Again, we knew which robot the person was looking at, so we updated the matrix, and we actually solved this problem using globally optimal. So in the sense that we actually knew for in each point in time which robot the person should look at to gain the most amount of information, and then we have some kind of metric, or actually the metric of how far from optimally curious that person is. Okay, and we use that. You have also local optimality and global and blah 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 and blah blah blah. Okay, and this is like the coolest graph ever. So what we have here is that we repeated it 6 times. So you have to know who's the friend of whom, and then again who's the friend of whom, and the matrix change, and you have to do that. What's interesting here is that the first, it's a very weird graph. So the y-axis, the x-axis is the repetition. During the first time, they didn't know what was the task. The human experimenter actually said, I have to do something, and went away, but the robot started to move already. So they didn't know what was the task, and we still looked at which robot they looked at, and then they repeated several times. The y-axis is very weird. It's the r squared of our behavioral measure, okay, how far are you from optimality, of how curious are you, to self-reported questionnaires of the people on their own curiosity and psychological inflexibility, also called social anxiety, like others see social anxiety. And what you can see here, because our hypothesis was that people who are curious will have this curiosity-driven behavior, and we were wrong. Initially, their behavior was actually correlated to the psychological inflexibility. And only after some time, actually curiosity popped in, which is very cool because like every educator knows that in order to be curious, you need to feel safe. You need to like not have anxiety. This is the first time we actually showed it dynamically with a person with quantitative measures. And because we actually did. Some academic related things, I wanted to publish this in a psychology paper. And the entire paper is only robots and math. So it took us like 4 years, but in the end, we managed. Why are you sending me all these robots? The whole point here was also the theme of the paper was you can run psychology studies with robots, social robots, and it's cool because it's totally reproducible. To run these experiments with people, I hire 3 actors and hope they will be good. Here I have full reproducibility, which is very cool. So we had this one, and then we had a single robot with a parent and toddler pair. So we have multiple robots and 1 person, now 1 robot with 2 people. I opened a startup because everybody had to open a startup at some point in their startup called Social Robotics, where we have a robot that teaches English as a second language to toddlers, age 2 to 4. But the cool thing about this age is that if you put a child and a robot together, one of them won't survive. So you also have the parent. So the robot actually interacts with the parent and the toddler. It's like a triadic interaction. And what is really cool is that we're actually not interested in the robot to see what should robots do. Parent and toddler interact better. Okay, so what can we do there? Our horrible competitors are tablets. And tablets are horrible, but they're even more horrible. So we compared this interaction between a parent, toddler, and robot, and a parent, toddler, and a tablet. And again, what we're interested in is the interaction between the parent and the toddler. And what we showed, like very easily, but we should have data for it finally, is that when the parent and toddler are playing together on the tablet, they just don't communicate. They both stare on the tablet and don't do anything. So we can actually see that. And with the interact with the robot, exactly the same interaction, exactly the same behavior, everything is the same. They look at one another, they have a lot of social interaction, they have scaffolding, they have much more fun, and stuff like that. But we video coded the entire interaction, and the thing that we can get if we video code the entire interaction, you can have a very multidimensional time series analysis, and you can start looking at causality. So we looked at Granger causality of all the interaction between the parent, the toddler, and the robot. And one thing which is very cool, the robot said at some point to the toddler, pick up the lemon. Okay, it asks it, but it's in English and the child doesn't understand, and the child picks up the lemon. But what we actually saw from the causality analysis is that there's no link between the robot asking the child to pick up and the child picking up. Everything is through the parent. So when the robot says pick up, the parent talks to the child, they nod, they do something, and then the toddler picks up the parent. So only by using this dynamical analysis, we can actually see what's going on and who's causing what and what's the thing that we can have there. I'm speaking really fast. I don't know how much time I have, but I have one thing. Yes, I have like 2-3 minutes. Okay, thanks. So now we have 1 robot and a group of children. So this robot is actually not a robot, but never mind, it's a puppet. And it teaches the roots of the Hebrew language to a group of children. My colleague, Dr. Goren, came up with a really cool idea to teach the root of opportunity in a very, very cool way. She went to the Ministry of Education, said that's a cool way. How do we clone you? So she came to me, I cloned her, and we put her own thing in the interaction, and they actually learn. You never see this where they start with like 20, get up at like 80% success. You never see this anywhere. So they actually learn the Hebrew roots. And there's another language in Israel that actually also has roots. It's called Arabic. And then it has more people in the world speaking it. So we actually taught Arabic roots to Arabic speakers. And next week we start to teach Hebrew roots to Arabic speakers. And it's in the schools for 2 months, operated by the teachers, which is actually cool. If you want to come to talk to me about scalability of social robots in the education system, you can do that. So we also had a robot that actually did this facilitating small group discussions in the classroom, and we went to schools, and it was very cool, but then it was March 2020, and no schools, so we pivoted like a good startup do, and we did actually an avatar for small group discussions in Zooms. So we came up with this whole setup where you have like the Zoom, and you have the actual activity that you learn in class, and you have the avatar that actually has a lot of algorithms on how to manage the class. For example, if someone is not speaking, then say please ask him. And if someone is speaking too much, say shut up. No, it never says shut up. Instead said, let's listen to other people. And we ran this study. Again, we have a lot of data. Yes. So we have a lot of data, facial expressions, and how much is it speaking. So we have also objective data on what's going on. And we ran a study with the avatar and without the avatar. So that's anecdotally, without the avatar, just took out this phone and started playing with the phone, even though they knew we videotaped them because they were children, who cares? But with the avatar, they didn't do that. So it's not that they thought it was better, but they actually felt that they listened to other and they talked more when the avatar was there, because the avatar actually facilitated a good discussion. But we also have this objective data, so they spoke more with the avatar, they were happy with the avatar, they were more engaged with the avatar. The problem with all of these agents is that a one shot is not good, so we ran a long-term study for 6 weeks. And now we're doing it with 8 weeks, and I don't care about the numbers, you just see that they don't go down, which is what's important in long-term interaction. And we're actually, the cool thing now is that this avatar is teaching social emotional learning for children, which is counterintuitive because the avatar is teaching them how to manage their emotions. And it's actually better than a human because they don't feel judgmental when they're actually speaking with the avatar. And I think I'm done. Yes, thank you very much. Question? Oh, I'm here. Yes, yes, of course.
If you can explain the difference between optimal curiosity and knowing what to do, because it seems like if you know who you should look at, it's no longer curious because you know the answer.
So the concept of curiosity here is what your action should do to optimize the information that you get.
Okay, so information.
It's the information content.
Okay.
So that's the point. That, and the concept in my take on curiosity, is a lot of people doing curiosity these days, is that you learn the optimal, I call it in the end exploration motor primitives. You actually converge to the optimal exploration. Usually exploration is random in reinforcement learning, right? When you have exploration, you have random, and then exploitation. Here you actually optimize the exploration policy. So you explore in the optimal way.
I think we talked about the implicit motivation.
Intrinsic motivation.
Intrinsic motivation.
Yeah, so that's it.
Yeah, okay.
Okay. Yes.
The thing with the, like, you don't have enough data to learn, and this is why. Yeah, you don't have simulation of children's faces, and this is why you have to have a huge learning rate. These days we have all the world models from like a Dreamer V1, V2, V3. Maybe you can we can learn what's the world, and then stimulate dream and
so specifically for that scenario, you cannot have it because it's personal to that specific child. So even if you simulate a child or you know something about it, then you personal to that specific child. So you learn a policy for that child, and you cannot simulate that child, otherwise you wouldn't do that. So in this specific scenario, when you personal to a specific agent, then you cannot simulate it. Because if you knew everything about that agent, then again, we knew everything.
You collect data. At the end, like, you will have enough data to kind of approximate what's done.
Yeah, again, on that specific child.
Yeah.
Yes.
But again, like we said before, you have like all the children have something in common,
Yes.
and then you can.
So the approach is like cloud robotics. So you have a lot of robots, a lot of children. You do like the optimal policy for the average child as a starting point, but you still in the end want to do personalization, which is a reinforcement learning on that specific child, and this you will never have enough data. I mean, you can start collecting it, but it's one chance. Okay.
Thank you.
Thank you.